All right, our second lesson in our final unit here focuses on the areas of sectors of circles and segments of circles. It kind of picks up where we left off with finding the lengths of arcs and essentially just sort of applies that same concept to area of parts of the circle. Insofar as radii are involved and central angle measures are involved. So again, this is going to require that you have an understanding of how to find the area of a circle, and again, how to work in terms of pi. And so when we take pi times the radius squared, we get the area of our circle. We then are going to find a fraction of that area of the circle as it pertains to the measure of that central angle. So one little initial exploration is just to kind of have this understanding of area and recognizing that when we're talking about squaring our dimensions, squaring our radii, we are exponentially increasing the size. And so just a real quick thought here, and we all love pizza, and if we don't, I don't know, I don't know what that means about you in your life, but if I'm talking about the medium pizza that's 12 inches, that means that's a 12-inch diameter pizza, which means that it has a radius of 6, which means that we have 36 pi, square inches. Now, this doesn't mean much to people when we talk about in terms of pi. Algebraically, it is helpful to work in terms of pi, but getting to the nitty gritty here, this is approximately 113 square inches of pizza, all right? When you are dealing with a 12-inch diameter, like medium-sized pizza. But for the large pizza, we have the same formula, pi times that radius squared. In this case, the radius is 8. And so we end up with 64 pi square inches. Let me look at the difference here from 64 to 36. It's almost double, right? 72 pi would be doubled, all right? And so here's what's going to happen when I do 64 times pi in the calculator. It gives us about 201 square inches. Look at the difference there. When you buy the large pizza, you make sure that you can have enough food for leftovers. Now, that being said, maybe we shouldn't be so wasteful here in America, but just kind of thinking about how much larger, how much more area is included just by increasing the diameter by a few inches, we find out that the difference there between your medium pizza and your large pizza is a very significant difference in the amount of pizza that you're getting, but probably not a significant difference in price. And so consider that. For all you folks who love to eat pizza. We're going to be talking about eating slices of pizza, specifically in the context of kind of this general idea. How much of the pizza are these slices? A sector of a circle is basically a region that is bounded by the circle itself and two radii. All right, so we'll refer to this as a sector of a circle. There's an arc, there are radii involved, and then that area that's captured is referred to as a sector. Now, the white space here in this circle is also a sector. All right, it's also a sector. It doesn't just have to be something that's smaller than a semicircle. It can be a sector that is included between two radii and a major arc. All right, so keep that in mind. The way that we find the area of the sector is the same way we found the length of the corresponding arc. We would find the length of the arc by taking this fraction over 360 of the circumference. Likewise, we're going to take the measure of that arc over 360 multiplied by the area to find the area of the sector of the circle. All right? And so in this case, if we're going to find the area of this sector that is found between points Z and M on the circle and the center O, then as we approach this, we are going to find the area of this sector by taking the measure of arc ZM, two letters with the little hoop there, two capital letters, over 360 multiplied by pi times the radius squared. And so the area of this sector is going to be 72 over 360 multiplied by pi times the radius squared. All right, and so this becomes it's like 1/5 of 400. All right, is how we're going to do that. 1/5 of 400. We should get about 80 here. Let's do 72 divided by 360 times 20 squared, and we get 80 pi square centimeters. All right, again, when we work in terms of pi, we multiply everything except for the pi in the calculator. 72 divided by 360 times 20 gives us 80 pi square centimeters for the area of this sector. The area of the circle would be 400 pi, and this is just a fifth of that. The 72 over 360 is just a part of a fraction of that whole area. So this slice of the pizza pie represents 80 pi compared to the whole area, which was going to be 400 pi square centimeters. All right? And so moving on to another example here, I would love to see you do this one. Take the arc AB's measure multiplied by the radius squared, and go ahead and compute the area of that sector. We can converse about this in class. The next portion, just to kind of speed things along here, if you need to pause the video and go back and finish that example, please do that. A segment of a circle is part of a circle that's bounded by an arc and a chord, all right? So this is called a segment of a circle. It looks like Eric Cartman's hat, if you're a South Park fan. And that's not an endorsement, you know, so, but hey, I'm just saying. That's kind of what that looks like. So a segment of a circle is bounded by an arc and what's called a chord. That segment that connects the endpoints of the arc is referred to as a chord. All right, the largest chord in a circle is a diameter. Every other chord is smaller than that diameter, or shorter than that diameter. Now, the way that we find the area of a segment of a circle is we take the area of the sector, which we just practiced how to compute, and then we subtract the area of this triangle. All right, there is a triangle here. And when we subtract the area of this triangle, we're left with just the area of that segment. Now, finding the area of the triangle is the tricky part here. I know that this is new, and that finding the area of triangles is old news. We've done that 4 units ago, and we've done it in the last couple units with trig and with surface area and volume. And so when we're dealing with triangles here, this is actually going to be the tough part. This is going to be the easy part. You're going to get familiar with this, and this is going to feel very comfortable, but this is going to be tough. The reason why it's tough is because we are dealing with an isosceles triangle. And so finding the area of that isosceles triangle, again, is 1/2 base times height. And we need to figure out we need to know the length of this chord for the base, and then the length of that segment will be the height. Right, now the good news here is that we're going to get to employ some previously learned skills and concepts. So that's the bonus. It's like, yay, we've done this before. But it's also the challenge because it's like, hey, we did this before, but it's been a couple months. And so you might have to reference your notes from Unit 7. I would look specifically at lessons 7.1, 7.2 with Pythagorean theorem, and 7.3 with special right triangles, all right? We've been dealing with special right triangles since February, and so we want to make sure that we can still handle that even here in May, all right? We don't get a final exam this year, but, you know, whatevs. There we go. All right. So finding the area of the segment. So I'm going to do one of these, and then I'm going to have you do the other. And so for this one here, we are going to find the area of the segment. So the way that we're going to do that is we're going to find the area of the sector minus the area of the triangle is going to give us the area of our segment. All right? So our area is going to be found by taking the area of this sector first, which is going to be 120 degrees out of the 360, multiplied by pi times our radius squared. Then we're going to subtract the area of our triangle, which is 1/2 of base times height. Now here's the deal. I don't know the base and I don't know the height. I know the sides of this isosceles triangle. If that's 24, then this is 24. But I don't know the base of the triangle, and I don't know the height of the triangle. So how am I supposed to find the area of this triangle so I can subtract it from the area of the sector so that I can get the area of the segment? Whew, there's a lot going on. And so let's bring it down a notch, let's reel it in, and let's look at this triangle insofar as we know what we are wrestling with. When I draw in this altitude in an isosceles triangle, which this is because these are radii and so they have equal length, when I draw in this altitude, it bisects the opposite side and it bisects this angle. All right? So that 120 degree angle just got cut into 60 and 60. All right? So now I've got a 60 degree angle. This is 24 feet. How can I know the lengths of these sides? Well, I can use my 30, 60, 90 rules. We should remember our 30, 60, 90. I kind of spoiler alerted that for you right here. Here's 60 degrees. Here's 30 degrees. This would be x, the short leg. This would be 2 x's, the hypotenuse. And this would be x times the square root of 3 for the length of the long leg. So in this case, if the hypotenuse in this triangle is 24, then that means that this would be half that. It would be 12. And if this is the short leg, x, then the length of the longer of the two legs, the one opposite the 60-degree angle, is going to be that short leg length times the square root of 3. So doing a little bit of Unit 7, Section 3, please, in your best interest, you need to know those things. Go back and look at those notes. You've uploaded them to Google Classroom, so they should be present. We now know the length here is 12 square roots of 3, so we know the length here is also 12 square roots of 3. When we add those together, we get 24 square roots of 3 is the base of triangle AOB. All right, that's this whole length right here is 24 square roots of 3. The height is 12 feet. So we can actually put in those values for the base is, 24 square roots of 3. The height is 12. And now we get to do our computation. We're going to work this, which is in terms of pi, this, which is with a radical. They will not be able to combine. This is going to be subtracting that, so we're going to do this one first. 120 divided by 360, or a third of 576, or 24 squared, leaves us with 192 pi. Next, we are going to subtract. Before you get all worked up in the calculator of like, how do I do this? There's a radical. Same thing, 1/2 times 24 times 12, all right? Leave off the radical when you're using one of these calculators unless your calculator can handle the radicals. Or think about it in your head. What's half of 24? That's 12. What's 12 times 12? I know that because I know my times tables. That's 144 times the square root of 3, all right? There's your answer in square feet, okay? So your job is to find the area of the sector, the area of the triangle, subtract, all right? Now, the funny thing is that I'm not approximating this. We're finding the exact answers here. Part of that is designed specifically to make sure that you are getting ready for Algebra 2. We're a couple months away from you starting that. Working in symbolic math is a fantastic thing to do. If this were an x and this were a y, we'd have 192x minus 144y. We can't combine those, leave them separate. And don't wrestle too hard with that concept. All right, so what I want you to do now is I want for you to be able to find the area of the segment in this circle. It should be a little bit easier, but go ahead and give that your best shot. And then upload those notes to Google Classroom. I did 2 examples. You're doing the other 2 exercises. We'll check those when we get back together in class.